Good morning, good afternoon, and good evening, and welcome to this presentation for the paper RGB-D Mapping and Tracking in a Plenoxel Radiance Field, created in cooperation between the Norwegian University of Science and Technology and Mobile Tech. I'm sure many of you are already familiar with radiance fields, like the ones used in NERF, but to explain it very efficiently, radiance fields are represented by continuously implicit functions of density and color. Using a differentiable model and combining it with a differential rendering equation, and multi-view consistency allows for the training of these models from post images, creating an impressive model for novel view synthesis. We first want to highlight the difference between novel view synthesis models and 3D reconstruction models. NVS models represent the appearance of a target scene and can be trained with only RGB information. It gives no guarantees for the geometry of the model. This means that NVS models are not very useful for practical tasks like robotics and XR, which usually require a geometrically accurate model. You might have seen that some NVS models produce good geometry in the form of depth images. These are usually special cases, trained on a scene with significant gradient coverage, or an inward-facing scene where something akin to space carving is happening. This will not hold for the general case, and performing RGB tracking on such data will only be valid within the coverage area of the camera pose distribution within the training image set. As soon as you go out of that distribution, the warped geometry will quickly produce very warped results. To make a model for NVS have accurate geometry and ensure correct projection of the known scene even outside the training distribution requires a depth prior. A depth prior that can explain gradientless regions of the scene where information theory tells us it's impossible to attain any geometric information from only an RGB image. Such a prior can, for instance, be a planar assumption, a dense depth predicting neural network, or simply an RGB-D sensor. The deceptive thing about novel view synthesis models is that even with wrong geometry, they produce accurate appearance, which causes us humans to hallucinate the geometry, like you see in the image on this slide, where the model trained on RGB images on the right produces very good appearance, but still has very incorrect geometry. The reason why we highlight the deceptiveness of an NVS model is because we wish to use radiance fields as a representation for tracking and mapping tasks, like simultaneous localization and mapping. And to do that, we need to ensure correct geometry. Some recent works have been performed related to utilizing radiance fields as representation for SLAM tasks. This representation is one of the simplest successful dense representation for SLAM and has achieved reasonably good results. However, the reliance of a depth sensor limits them to indoor environments, and their volumetric nature and need for a neural network significantly hinders computational speed of the model. We build on these methods by formalizing the math and improving the results. Our contributions are as follows. We have first demonstrated the need for a dense depth prior for dense SLAM systems. We also produce a model-agnostic formulation for mapping and tracking using volumetric rendering equations. We present an algorithm for RGB-D mapping and tracking in a voxel-based radiance field. And we improve the state of the art for both mapping and tracking tasks. We propose a method based on a voxel grid model for novel view synthesis. We extend the mapping algorithm to also use depth data based on an RGB-D sensor to ensure good geometry. And we develop a dense image-to-model alignment based tracking algorithm, also using the RGB-D sensor. As mentioned, as opposed to all previous works combining SLAM and novel view synthesis, we calculate the analytical derivatives for all equations and don't rely on the autogradient libraries like PyTorch. We also implement these directly in CUDA for fast optimization. As hinted at, we did not use a neural network to represent our model, but rather build on a voxel grid representation developed by Frederick et al. Representing the radiance field as a voxel grid allows for direct data access, and results converge 2 magnitudes faster than in neural network variation. In the voxel grid, each vertex is represented by a density value and a view-dependent color value. The color values are modeled as the constants in spherical harmonic functions, and any value between the vertices, both density and color, are calculated by linear interpolation of the 8 closest vertices. The voxel-based radiance field model shares the same differentiable volumetric rendering equations as all modern volumetric novel view synthesis algorithms. The equations explain how much light and what color is reflected from any point along a ray back into a camera pixel. It is calculated by iterating over the ray and checking how dense a point is and keeping track of how much light is already returned. Based on the density and the remaining light, some amount of color is added to the final rendering pixel color. The same equations rendering color can also be tweaked slightly to instead render the expected depth value. This is done by swapping out the color from the sample points with a distance value from the camera, scaled between 0 and 1, which will effectively render a depth image if done for all pixels. During the mapping process, we use a combination of both color and depth to give our model accurate appearance and geometry. For a mathematical overview, we enter the partial derivatives into an overview slide. We only show the partial derivatives of these equations to keep it simple and generalizable. If you're interested in exact results of these partial derivatives, please have a look at our paper. Tracking is performed by image model alignment, adjusting the camera parameters such that the view rendered from the model corresponds with the input image. Conveniently, both the color and depth rendering functions are not only differentiable with respect to the map, but are also differentiable with respect to the sample points, which is differentiable with respect to the ray and ultimately with the camera parameters. We calculate these derivatives by using an alternative version of the chain rule as shown on the slide. It is possible to track using only RGB or only depth data, but we found it best to use both as it combines the lower frequency depth signal with the higher frequency color signal, which leads to a high pose accuracy and a wide radius of convergence. We also added derivatives for tracking to our overview slide. Combined, these formulas encapsulate all dense mapping and tracking systems using volumetric rendering equations, utilizing either RGB or an RGB-D sensor, no matter what kind of model representation is used. The derivatives of sampled color and density with regards to sample position is given by the select model. The derivatives of the rendered color and density based on sampled color and density are given by the rendering equation. The remaining partial derivatives are always the same, giving us a general formulation for mapping and tracking systems utilizing a dense volumetric model and rendering equations. Adding the equations for depth-based mapping and RGB-D tracking to the voxel-based radiance field, we compare the results of the separated mapping and tracking tasks with the current state-of-the-art systems. The mapping results are presented visually at the bottom of the slide, and the tracking results are given quantitatively at the top right. All systems were time-constrained in both tasks. You can see that both the quantitative and the qualitative results showed a marked improvement over the state-of-the-art while simultaneously being faster. Thank you for listening. If you want more details, please check out our paper.